no! Testing, testing. We are golden. Ow, that hurts. Good morning and welcome to our first lecture in this course. We are going to still have an introduction to a large degree, where it's not really about test questions and things like that yet. It's just getting the conversation started with inductive reasoning because it's the necessary first step, but not a lot of, or really any significant testable questions will come out of it.
आन लग रहा है बल्कि ओ बैंड जो चार वो बंदा नहीं मैं लेट गया ऊपर ही
Someone's mic is on. If you are speaking to me or the class, great. Otherwise, you have to mute your mic and or use push to talk. But if you have a question as we continue our discussion, absolutely speak up, interrupt me, ask any questions you may have. Otherwise, I'm gonna have to mute you. All right, as we go, I would appreciate if, because we're still starting out, there might still be administration questions or issues and things. We spent the whole of yesterday giving everyone a chance, as well as the whole week before, really, to try and sort out how this course is going to go. So any issues that still remain, absolutely ask them, but let's leave them at the end. This won't be a full 50-minute lecture, so we should have time to address all those things. But any questions specific to the topic, feel free to interrupt as we go whenever you are confused, whenever you feel we're going too fast, if we're going too slow, anything, uh, any questions you might have. Otherwise, we will continue as soon as I just get confirmation in the chat that you can both see and hear me, just because I'm paranoid and I never know that on your end things are what they should be. I always have this idea of having some technical issue I don't realize, and then I'm actually speaking to myself for half an hour, and everyone's just sitting there quietly, not wanting to say anything. All right, perfect. Also in the YouTube chat, there are 26 people watching. If someone can just let me know, perfect. Okay, just my paranoia. You never know. It hasn't happened yet, but one day when I don't ask for confirmation, that's the day when some technical issues will come up. Okay, so we have this game, sort of an older game called billiards that we can use as an introduction for the concept of inductive reasoning, where you have a table and you shoot balls and they bounce off the sides of the table uh, to hit other balls and so on. Now, the actual rules of the game are not important for us. It's more this idea of a ball bouncing around inside a rectangular area, and that creates a path that the ball travels on. Now, what often happens in a mathematical situation is we simplify and idealize the situation. And what we're going to do, just want to check that I can scroll correctly here. There we go. What we're going to do is not think about the realistic situation, but think about just using the idea to create a scenario where we are just going to have one ball and we are just going to assume it's going to travel around the table indefinitely. So if we have a 10 by 5 or 5 by 10 rectangular table, let's simplify the situation by saying we're always going to shoot the ball from the bottom left corner. These little squares are going to help me track the ball. It's always going to go at a 45-degree angle. We want to simplify things so we can better and easier and have an easier time to understand it. So always 45 degrees, and then we can track the ball, and it's only going to stop when it hits a corner point. Then it doesn't bounce right back. That's sort of the black hole that catches the ball. Any other time, it's going to keep going forever. So we ignore friction and anything like that. So in this left table, let me just close the door because someone is mowing the lawn and it might be a little noisy. I will be right back. All right. Hopefully that helped a little bit for the background noise. So if we have our 5 by 10 table, just as a random example, the ball is going to travel from the bottom left always, bounce on the side here, and because it's always going to have a perfect bounce, it's going to end up in the top left corner. If I change the table dimensions to a 6 by 10 table, now the question is, how is the ball going to move around the table until it hits a corner point? Because that's the only place where it can stop. So let's think about that for a second and see if we can track the ball. It's going to start on the bottom left, track, track, track over here, and then bounce back and keep bouncing because it hasn't hit a corner point at the top here. Keep going, and I have to draw it out until it hits a corner point. Let's see what that looks like. So if the table dimensions change, the path of the ball could be significantly different from one table to the next. In the 6 by 10 table, the path is much more complicated, and eventually we keep going until, in this case, it hits the top right corner. So very different. So then the obvious question uh, becomes, how do the table dimensions affect the path of the ball in this situation? Different table dimensions, potentially completely different path. But maybe there are other table dimensions that give me similar path. So now we're going to go to our first example or exercise, which is exercise 1.1. Let me zoom in a little bit. Now, the first part of the exercise here just explains the situation we've been working with. And now we have a bunch of just random uh, table dimensions. Again, I remind you that if you want to say something and ask a question, perfect. Ask it at any time. But if you are not planning to say something, your background noise could be a disruption, so either mute your microphone or use the push to talk function in Discord. So we have these table dimensions, just randomly selected. We just have some examples. Now the question is, how does the path of the ball work on each one? Always bottom left. Can I figure out the path for each of these tables? So because we have the time, it's not a full class, it's still part of our introduction, I will give you some time to figure out what the path is for each one of these table dimensions. But it's important that you actually start exploring, start doing something. It definitely enhances the learning process by actually exploring, experimenting, trying something yourself, compared to just sitting back and waiting for me to give you the answer. It doesn't really sink in the same way. So we'll take some time. Let's pick time here. What time is it now? 10:40-ish. We'll take, let's say, take 5 minutes to give you some time to figure this out and see if you understand the situation and if you can find the paths for each of these tables, or at least some of them. So let me just set the time here, and I'll show the time on the screen so you know when we will be starting again. All right, I'll do it this way. There we go. Now you should see when we will start again. So take the time and find the paths for those tables. All right, we are back. Now, sometimes when I pause to give you time to do something, I mute my microphone and I might forget to unmute it. So if you ever think I should be speaking and nothing's coming through, let me know if you think something is off. But otherwise, I'll assume that everyone can hear my voice. Okay. So hopefully you've gotten somewhere into this collection of examples and you found the following paths. I'll try and zoom it. Almost. This is so small. Man, can I not? Hmm, can sort of see. I'll scroll up and down. We can't see them perfectly. Okay, so for those that want to share, did anyone get at least some of these paths? And do you have any questions about how these paths are obtained? Any feedback will be good so I know that I am making sense. Any questions so far?
So far, so good.
All right. Yeah, so even if you don't have a question and it makes sense, because I don't see any expressions of agreement, it's also good to just say, yep, we're good, keep going, and all that. Okay. Now, I just guessed 5 minutes. You might not finish the whole thing, especially looking at this 5 by 7 table. That might take a while to not to keep everything in line and not make a mistake. But regardless, it's just some examples. We could have had 4 examples. We could have had 20 examples. These were just randomly selected. So now if we look at our book, we have some follow-up questions. I'll try and zoom it in here. Now, whether you open the book, I'll mostly try and show it on the screen as well for the most part, but you have access to the book. So the first question here in exercise 1.1, for what table dimensions does the ball have the simplest path? And does it make sense? Why do you think that is? So we definitely want to have sort of a conversation, even if I ask an obvious question. Uh, it's not me just lecturing you, it's more of a conversation for many of these. Where's the simplest path? The, the square one, yes. So does that make sense?
Yeah, makes sense.
Makes total sense because we stop as soon as we hit a corner point. If it's perfectly square, we're just going to go straight to the diagonally opposite corner point. Just a reminder again, I'm happy anyone speak whenever you want to speak, but if it's just background noise, make sure you mute your microphone, use push to talk, otherwise I mute you and you can never speak again. I'm kidding. But I might forget to unmute you. I don't think if I mute you, I don't think you can unmute yourself. So I don't want to do that. I might forget. Okay. The next question. Oh man, this lawnmower is super annoying. I don't know if you can really pick it up on your end, but it sounds really loud to me. I'll try and speak louder.
No,
Oh,
it seems okay.
okay, good. Okay, second question. For what table dimensions does the ball travel over every square? I definitely see some here, yeah. Every single square. We have a cup. We have a few, yeah. We have a 2 by 3, this top little guy. We have the 2 by 5, also traveling over every little square. 3 by 4, not 2 by 6. No, we're missing some squares there. The 5 by 7 one, which if you did that, that might have been a lot of work. But not all of them. Certainly not all of them. So there are some. Okay, I don't know what that was, but that gets mute. Yes, let's not have that again. That hurts my ears. Now I am old and I can't hear that much anymore, but still, that was loud. So, some have the property that the path travels over every single square, and some don't have that property. So we can definitely separate all tables into 2 groups, one having that property of every square and one not. we can, from our examples, make a list of all the tables in our example collection that have that property. But the goal here is to use our examples to make general statements about all tables. I can't go and draw every single different table dimension possible. I will always have a limited number of examples. But can I use those examples to make a wider general conclusion? That's really what inductive reasoning is about. And in this example, we can sort of start that thought process. So number 4 asks, can you think of a rule for telling in advance if the ball will travel over every square of a table without drawing the path? So we want to use our examples and say, not only for these few examples does the ball travel over every path, but if any table looks like blah, 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 the same property will be true. So now I'm very dependent on the examples that I have, and I hope that they are sufficient, they are enough variety for me to be able to get to that general conclusion. So in this case, we only have 1, 2, 3, 4 examples where the ball travels over every path. Now, that might be enough in some cases, and in some cases it might not. That's sort of the downside to working with examples. How many is enough? So in this case, we can maybe. It's not expected that, oh, I have to see this right away. No, I'm sort of at the mercy of my examples. In this case, a possible conclusion could be that I see that the ones that have a path over every square, 2 and 3 are the dimensions. 2 and 5, 3 and 4, 5 and 7. Okay, so there's a relationship between these dimension numbers. And the others don't have that property. 3 and 9, 4 and 6, 6 and 6, 2 and 6, 4 and 10, 9 and 12. So maybe some of you have noticed that if the table dimensions do not have a common divisor or a common factor, then the path goes over every square. And as soon as they have a common divisor, like 4 and 6 have a common divisor of 2, 2 and 6, 2, 6 and 6, well, 6. 3 and 9 have a common factor of 3. 4 and 10 have a 2. 9 and 12 have a 3. Then the path misses some squares. Now, again, I'm at the mercy of my examples, and I don't know 100% if this conclusion, this observation is true for any table. And I will never truly know because I can't go and draw every single table. But that is the answer in number 4. It turns out that the rule is that the table dimensions, if they don't have a common uh, divisor, then the path will travel over every square. Even though I give you that answer, you don't have to feel that, oh, how was I supposed to know that? That's impossible. It should kind of feel a little uncertain because we have so few examples. Now, I will certainly feel better about that conclusion if I were to go put in the time and draw 100 different tables, 1,000 different tables. I'm going to feel more and more confident in that conclusion. But I'm never going to be 100% because in some weird situation, there could be an example that I just miss that contradicts my conclusion. But certainly, the more examples I have, the more confident I am in that conclusion. Okay, so those are just the questions again. So the idea behind inductive reasoning is exactly that, that I'm collecting evidence, I'm making examples, whatever it may be, limited evidence. I can't look at every possibility. And from that, I am noticing some patterns, making some observations. And then I'm using that to form a conclusion based on what I observe. But I am at the mercy of the evidence, of the examples that I have. Look at this poor little caveman. He says, water boils down to nothing, snow boils down to nothing, ice boils down to nothing, so everything boils down to nothing. So that means that if I don't have enough variety or just enough examples, my conclusion could be way off because the examples lead me to that conclusion. Here's another little story that is typed up in the book as well. We have a scientist and he has a jar of fleas. So he opens the jar and he takes out a flea and he puts it on the table and he shouts at the flea, jump! And the flea jumps. Then he puts down another flea from the jar, puts it on the table, and he shouts at the flea, jump! And the flea jumps. And he keeps doing this, and every single time when he shouts, the flea jumps. Next, he takes out a flea from the jar, little barbaric, but he pulls off the hind legs of the flea, puts it on the table now, and shouts at the flea, jump! And the flea does nothing. He doesn't jump. He takes another flea from the jar, pulls off the legs, puts it on the table, and shouts, jump! And the flea doesn't jump. And he keeps doing this, and every time the flea doesn't jump. And then he takes his clipboard and writes the conclusion. Fleas with their hind legs pulled off are deaf. What do you think about that? Any thoughts? Was that a good story? Did you enjoy story time?
Yeah, it was a good story.
Oh, thank you.
Really good story.
Thank you. I really tried. I really tried. So you're really at the mercy, but you're at the mercy of your observation. And if you make certain observations or limited or not enough examples or sort of just think about it the wrong way, your examples and observations could lead you to a completely ridiculous conclusion that's just not true. So that's the downside of uh, inductive reasoning. There are pros and cons. The pro is that it's easy. Making examples is a good first step in problem solving. Make some examples, see what you get, see how the path uh, looks on the table, see what happens to the flea. It's easy to do. But the downside is that it is not 100% certain that my conclusion is correct. Let's write that down. Inductive, we haven't written anything down today. Inductive reasoning. Pro. Now you can probably come up with other pros, but a pro, the first one that comes to mind is that it's easy to do, easy to make examples. As easy as anything is going to be. It's easy to collect evidence. But a con is that I am never really 100% certain in the general statements that I'm making in my, let's say, general statements or my attempted conclusions. Let's say here, or conclusions. So the only thing we really need to know coming out of this first section on inductive reasoning is, what is inductive reasoning? Is it used? Is there an example of inductive reasoning? That another example? Well, the apple falling from the tree is inductive reasoning. It just so happens that the apple falls so many times and repeatedly, consistently falls from the tree that the theory of gravity, the conclusions that you make are sound and works in many other situations. But you need to be aware that you are limited to the examples that you're using to make those conclusions. So if you understand what inductive reasoning is, can name a pro and con of that reasoning, what's good about it, what's bad about it, then uh, you are good to go. Any questions so far? So I will say, for a lot of uh, our lectures, there's time built in for you to ask questions. And if you don't ask any questions, then very often we might be finished way too early. And I can't get to the full 50 minutes. And then I feel you don't get your money's worth. So you have to help me help you by stretching it to get to that 50-minute. Otherwise, we don't have enough to do. So you have a job too. Your job is to interrupt me. Okay, last exercise. It is number. Oh, this one. I wanted to say this. Oh, I almost forgot. Let's look at the billiard table example again. And let's suppose you made a different set of examples. Let's suppose you made these 7 examples, a 1 by 8 table, a 2 by 8, 3 by 8, 4 by 8, all the way to a 7 by 8. Okay, good examples. You looked at the path for each of these tables and you got this. Certainly some variety, certainly some observations we can make. And you make the observation that for every one of your examples, the ball ends at the top left corner, every single one. You then want to, because the examples lead you to that, suggest a conclusion that for every table, the ball will end in the top left corner. That's what your examples suggest. But that's not a correct general statement. It's not a correct general conclusion because we've seen other examples where the ball ends up in different corners. Though your example set leads you to believe something that's not true in general. That is the downside of inductive reasoning. Let's look at of course, there's a lot of other stuff here, just sort of emphasizing the concepts in different words that you're welcome to read, but the videos will be sufficient as well. Let's look at exercise 1.2. We have a circle. Let me zoom in. Can I zoom in some more? Yeah, I can. Okay. So we start with a circle, and then we put 2 points on the circle, connect the 2 points, and that line separates the circle into 2 regions. Then we take the circle and we increase the number of dots on the circle, connect all the dots, and those lines now separate the circle into 4 regions. And we keep going. We're collecting evidence, right? Now we increase the number of dots to 4 dots, connect all the dots in all possible ways, and that separates the circle into 8 regions. So far, the number of regions changed from 2 to 4 to 8. Now, so this is what we have so far. Number of dots, number of regions we get. Now we want to use 5 dots and eventually 6 dots. Zoom out a little bit. So there are circles for you. Take a circle, put 5 dots on the circle, or take some piece of paper. Just start exploring, start doing something. Get a pen in your hand. That's how we learn. Put 5 dots randomly on the circle, connect them in all possible ways. Maybe use a ruler, it might help, it helps me. And see how many regions we get. That is your task. Is there anyone who is not sure what is happening in this exercise? Because I'm going to give you some time to make 5 points on the circle and count the regions, and then 6 and count the regions. We just have to draw. The more dots there are, the more careful we have to be in our lines. We want to make sure we have as many regions as we can. 5 dots and 6 dots. Is there anyone who does understand what we are doing? As confirmation that I am making sense. I need constant confirmation. I'm very insecure. I need constant validation.
Makes sense.
All right, good. Whew, that's a relief. So it's time for you to get whatever drawing device you want, whether it's old school, pen and paper, maybe pencil, because it could be tricky, or do it electronically, do whatever you want to do. But let's see how many regions 5 will give us, and then how many regions 6 will give us. I will say, just before I leave you to it, there's just one thing we want to be aware of, especially with the 6. If I have a circle, I want to make sure that I maximize my regions. So I don't want to space the 6 dots perfectly and have a situation like this. So those will be 4 dots so far. And if I put the other 2 dots perfectly here, I could have a situation like this, where there's a region there that I'm missing. This guy should be a little off so that I maximize the regions like this. Otherwise, I could miss that region. So only 2 lines should intersect, no 3 lines perfectly. So try and space your dots in a less ideal way. So otherwise you might miss a little region. Okay. So just be aware of that. Now you might only get, I want to get at least to the 5. I want to finish the 5. The 6, it takes time. Uh, so we don't have much else to do after this. So I'll give you 5 minutes. Let's set the time here. What is it now? Let's go to 11:15. And then we will wrap it up after that. 30 seconds. Exciting there. All right. We are back. You don't submit it, you just do it for yourself to take part in the experience that is math, or something equally philosophical. So let's see what we get. So when we do the 5 dots, focus on the 5 dots. How many regions do you get? 5 minutes would have been enough to get the 5 dot one done for sure. Did anyone do it? Did anyone get a number of regions
I got
for
16.
16. Let me write that in actually here. Let's see if I can fill it in here. 16. That's sort of 16. Perfect. Can anyone confirm the 16? Oh, lots of 16s. Perfect. Now five circles. 5 circles. 5 dots. It's doable. It's not hard. You can totally do it. So now let's just think about this. Let's suppose we stop here and we don't bother with the 6 because I'm lazy. I don't want to do that many drawings. I'm looking for a pattern. Complete the pattern. 2, 4, 8, 16. This is where you say stuff. I'll do it again.
32.
2, 4, 8, 16, 32. So if I were to stop there, let me put it like this. It's not it's not confirmed, I think. If I were to stop before the 6, I have my examples. I could make the conclusion that the number of regions is a power of 2, based on the number of dots, of course. However, let me close this. If I did the 6 dots carefully, correctly, try as I might, sorry, that's something else. Try as I might, I do not get 32. I get 31. Unfortunately, it's 31. So there is a big difference between what we want and what actually is true. And if your examples are small, few, limited, or sort of cherry picked to get me where I want, it might not be the actual truth. And the relationship between the number of dots and the number of regions is actually much more complicated, even though it's a very simple to understand situation. It is just not 32, it's 31. And then, of course, the more I do, the further away from a power of 2 it gets. As much as I want it to be 31, it's not. And it'll never be 32, I mean. As much as I want it to be 32, because that would give me an awesome pattern, it's just not. It's 31. And it just happens to be a much more complicated situation. So I'm at the mercy of my examples. And if I stop early, if I don't have enough examples, if I don't have enough evidence, what evidence I have could lead me in a direction that is simply not true. Simply not true. So that's the downside of inductive reasoning. I have to sort of overcompensate and make sure I have enough examples, enough variety, so it's really representative of the situation, so that my conclusions um, are not 100%, but increasingly more confident I can be in those conclusions. All right, that wraps up our introduction discussion on inductive reasoning. Are there any questions on inductive reasoning specifically? And then we'll see if there are any administration issues that people might still have. Any questions on inductive reasoning? Does it make sense?
No.
No, it doesn't make sense? Or no, there aren't any questions? Sorry, that was totally my fault. I totally tricked you. I should only ask one question at a time. Okay, so I'll end the video there. I'll stay on in Discord if there are any administration issues or issues about the course you're not sure about what to do or when to do it or anything like that. But officially we'll end the lecture video and that'll get backed up to YouTube. All right.
Thank you.